All right. Is this IQ again? Eat more butter. Butter makes all things better. Sort of a haiku again, right? They use 6 syllables in the last line. I do agree with the sentiment. I'm not sure it's the second principle. The second principle, right? That's 6. First is 1 syllable, right? Second is 2 syllables. So we fixed their haiku. That's pretty sweet. Okay. Screen's down. What do I want? Left projector on. Maybe. Screen down. Sweet. All right. We're rolling. This is about where we left off yesterday, right? Here with the picture here. We've got our tool. We've got our workpiece. All right, it's going by over here. Chip going up like this. So we've got our T1. We've got our T2. We've got this alpha. That's our rake angle, right? And here we've got the shearing that's going on in here. And our shear angle here, right? So this is about where we left off yesterday in modeling. And so again, our workpiece is moving past the cutting edge of the tool, going this way. And we've got this resultant force coming down like this. Is that where we were? And again, why are we modeling our cutting process? Why are we modeling the cutting process? We'd like to estimate how much power it'll take. Why are we modeling the cutting process? So what's your name again? Corey wants to estimate how much power it's going to take. And is this the diagram we typically would use if we're going to estimate power? How do we, so here we've got a force, right? And we can break that up into a cutting force and a thrust force that's keeping the tool down here, right? What do we know about the cutting force? What do we know about the cutting force? As we're modeling our manufacturing process, what do we know about the cutting force? Anybody? Yeah. So, all right, it's impacted by the feeds and speeds. So what do we know about cutting force with relation to power? Because Corey wants to model power. He wants to estimate power. We know it'll be impacted by the feeds and speeds. Why do we want to, or what do we know? What do we know about FC with relation to power? There's dots in it for you. Tootsie Roll.
Is it that the force times the velocity, since the tool is moving in that direction, force times velocity?
So power equals force times velocity. This is our velocity over here, right? And this is the surface speed. So our surface speed, that's the speed at which the cutting edge of the tool moves through the workpiece. What does surface speed depend on? Yeah. So surface speed depends on feeds and speeds, sure. Specifically, what does it depend on? Nobody in the back wants to chance it, huh? That's not the answer I was looking for. What does it depend on?
Would it be your spindle speed?
So it does depend on spindle speed. What else? So what do you use for spindle speed? So RPM, which equals rev over min with all the letters. Who said that? Somebody said it. Oh, you're going to have to get up for that one. Try again. Revolutions per minute. So RPM. All right. So RPM, but RPM is not surface speed. What are the units for surface speed? Feet per minute, actually. So we get feet per minute. We got revolutions per minute. What do we need to know? Diameter will help us get there. So where's the diameter in this diagram? See this straight line here? This planar surface that's level in a straight line? That's just zoomed in on the outside of the part, right? So the diameter is down that direction somewhere. So we're just zoomed in so much on that part of the part that it looks like a straight line. It's like the earth in front of you looks like a straight line, even though there's a horizon, right? Right? So the diameter is in the rotation of the workpiece going past the cutting tool. So if we were to zoom out on this drawing, it might look something like this. We're looking at the end of the workpiece. If it was a turned operation, if we're looking at a lathe. And here's our cutting tool. And so as the workpiece comes around, right, this part is the uncut chip thickness. It's about to get cut. Is that the width? So it's the width of the uncut chip. But so that's about to get cut. It's going to hit this, and it's going to flow out on the rake face of the tool right as this happens. So our diameter is coming out like this. And so diameter times. So modeling of manufacturing processes, modeling of any process like this is often creating an equation. So diameter times, yep. Yeah. Pi times RPM. And then we'll have to go from, so our diameter is typically in inches, right? And our RPM, or what we're looking for surface speed, is typically in feet. So we got to add a factor of 12 in somewhere to convert from inches to feet. Okay, so our velocity, is velocity a dependent or independent variable? Large Tootsie Roll. Is velocity a dependent or independent variable? Right? It's a process variable. We get to choose velocity because we choose RPM. We may or may not choose diameter, right? The final diameter of the part's chosen by the designer, not the manufacturing engineer. We get to choose how many steps we take to get to the final diameter, though. So along the way, we choose what the diameter is. Or if it's a milling operation and we're choosing the tool, we choose the diameter every time. All right, so FC times velocity equals power. What else does power equal? Yep.
Work over time.
So power does equal work over time, right? And that's how we get to this equation. But if we wanted to estimate the power, so when we're doing this here, we could pick the velocity, but what's the force depend on? Yeah.
Everything else going on there.
Yeah, the force depends on everything else that's going on in that picture, it especially depends on this, the transition that's going here where it was workpiece and now it's chip, right? Would you be willing to believe that there is a lot of energy in this plane when we transfer from workpiece to chip? The bit of the workpiece that's over here, it has no idea that it's about to be a chip. It's just bebopping around, just living its life. And then all of a sudden it slams into this shear plane and gets changed. It's sort of the change in life. And it's the change in life where you get smashed up against something and you come out a different shape, right? So that happens, we get chip flying off. That's pretty cool. I mean, I think it is. Do I? That question requires way more beer. Okay. So we're turning our thing. What else? So what is everything else in the picture that we're talking about when we're talking about what does the power depend on? What is the everything else we're talking about? We made a list yesterday, right? What are the factors that we care about if we want to estimate power? We can look up in tables and charts in the machinery's handbook, up in the back. So we care about, this one's risky. Oh, man, that wasn't even close. Slipped out of my hands. We'll try this way. All right. All right. One term, the ceiling's kind of low in here. It's really hard to get that parabolic trajectory to the back row. One term, there's a kid from the pitcher from the baseball team was in the class. And so I had him pinch throw for me. But it's not really the shape of a baseball. What did you say in order to get all that bombardment? I forget what the question was, but if you tell me the answer, I'll remember. Oh, okay. So the tool of the sharpness of the tool. I think we call that one W. How sharp the tool was. So the tool wear factor, that's where the W comes from. So what else did we care about? Yeah. So the machinability of the material properties. We get this KP value. And we look that up in our machinery's handbook. What else did we care about? Yes. Material removal rate. Almost. I was going to do a second one, but she wasn't looking after that. Material removal rate. We call that Q. And what else do we care about? There's this feed factor. We call that C. And feed factor, who was it? You better duck. You get safety glasses? Oh, almost. And so power equals KP Q W C, right? Times. It also equals force times velocity. What do you remember about, what, like 7th grade math? What do you remember about 7th grade math when you have two equations?
You can swap them out.
Yeah. If you have two equations, you can have two unknowns, right? So that's cool. So if we know something, we can solve from one to the other. So that's kind of cool. So we can estimate our power. We know what our velocity is. So if we estimate our power and we know what our velocity is because we got to choose it, we could estimate the force, right?
I was wondering, do the material properties change a lot, like with heat? I know a lot of the small parts are relatively hot.
Yes, material properties change a lot with heat, but the KP value that you're looking up in the machinery's handbook is found experimentally. So it was determined in the same condition that you'll be doing the cutting-ish. I mean, so this is an estimate again, right? So it'll get you in the ballpark. It'll get you close, but it won't be the definitive answer. It'll just, like, often you do things like this to keep from crashing the tool on the first attempt, right? To keep from exploding the tool the first time you do the cutting operation. One of our students, what's that? Sure. So W is our tool wear factor. So it's basically how sharp is the tool. We looked this up in a table from the machinery's handbook. KP is a machinability factor that has been determined by thousands and thousands of experiments that people have done and written papers about it, put the data together to do all this. Our material removal rate is just the volume, basically the volume of chips you're creating over time. So it's volume over time. In this feed factor, they again determined experimentally when they did their model and the graph of the results didn't quite match the graph that they expected, right? That often happens in experimentation. You do modeling. When you do a model, you get a graph of what the results should look like. Then you do the experiment and you get a graph that's sort of like the graph, but not lined up correctly. They figured out that there was this factor that depended on the feed rate. And so they had this formula to figure out what's this feed rate factor. And so again, you look these up in the machinery's handbook. It'll allow you to estimate power. Now, often when we're doing our machining, so this is like doing the machining. This is guesstimating before we get to do the machining. So often when we're doing the machining over here, so we've chosen the V, we've chosen the velocity, and we can adjust that. So if we want less force, we could change the velocity. If we want less force, what else could we do? So why would we want less force? Yeah. So if when you're cutting, the part flies out of the vise, that would be a reason to want less force. Or you think it might. Why else might we want less force? Yep. The part is deflecting or bending, and it doesn't come out the shape we want. Reducing the cutting force can reduce the tool wear also. Sure. And of course, the catastrophic tool wear. There's a couple local tooling manufacturers, and one of them had supported the lab a lot, and they were doing these tool wear experiments. And this is kind of cool because the tooling manufacturer needs to know how fast their tool is going to wear out. We're going to talk about this a couple weeks when we talk about economics. But if you wait until the tool wears out before you change it, you risk the tool exploding and damaging other things in the system before you change it. So you want to predict when the tool is going to wear out, so you can change the tool before it's completely worn out. Does that make sense? Yeah. And so one of the ways they do this is they cut for a little bit, and then they take the tool out and they look at it in a microscope. Then they cut for a little bit and they take the tool out and they look at it at a microscope. Then they cut for a little bit, right? And so you build up this pattern of how quickly does the material on the surface of the tool wear out. We actually we did I think it was an MQP. Nah, I think it was a kid working on a master's thesis. I can't remember exactly which one it was, but it was similar to that. But he made a little robotic system that instead of taking the tool out of the machine, he had a little robotic arm that would bring the camera over, and it had a microscopic camera on the end of the robot. And it would look at the tool before it came out of the machine. So they automated that tool wear experiment. So one of my colleagues here, he wanted us to do tool wear experiments during M1800 labs. Because we get a lot of people going through making parts on the machines. That seems reasonable at first glance, right? I said, no, absolutely not. And partly I did that because I know that that's like the answer he hates the most, right? You ever say something to your friends just to get them going a little bit? So I know he hates, his response to that is always 100%. I've heard him tell it to the registrar of the university. I've heard him tell it to the department head when they were in an argument. It doesn't violate any laws of physics, right? So why can't Workday, I don't know. What's the biggest problem you guys have had with Workday? Yes?
When you register for courses, you can't make your own schedule so that you can submit it all at once.
So you can't know what the schedule is going to be like inside Workday until after you've made the schedule and submitted it. So the question would be, why can't Workday work like I would want it to? And if you ask the people that implement Workday, they'll be like, it can't. We can't do that. That's not available in the software. But it doesn't violate laws of physics, right? If you could imagine it, it could happen. And so I know that that's his thought. So I said, no, absolutely not. We can't do that. And so he's like, why not? It doesn't violate any laws of physics. And I said, because our tool wear is always catastrophic. Because you guys don't wear out the tools, you break them. Because we put inexperienced operators in front of the machine choosing the parameters. So yeah, our tool wear is almost always catastrophic. Therefore, we don't do tool wear experiments during lab. All right. What time is it? Got time. I'm going to switch back over to the presentation. I finally learned how to do this in the online streaming software. It's transparent to you guys, if you're here, not if you're there. Back to the presentation. Who is that? You clearly need more sugar. All right. It always, every single, that was weird. Oh, yeah, I expected that. Did what I wanted, right? That's cool. Is that I hardly ever put animations in my slides because I feel like the slide should be about the content, not about the gee whiz factor. But this day, I went all in. Right, so let's look at the chip. As we look at the chip, we're concerned about the force that the tool, or the loads that the tool applies to the chip. So what do we know about it just looking at it from here? Turn on right projector. Right projector power on. How come it's not projecting? Right projector. PC. Now it's projecting. You can kind of see the stuff on the board, right? If I don't put the screen down. And if I erase. This part of the lecture works a little bit better with a whiteboard, but the chalkboard is so much more fun than a whiteboard. All right. So our tool is over here. It's pushing on the chip, right? Our workpiece is over here. It's pushing on the chip. Is that fair to say? Okay. So where are we going to see forces to do with this chip? So our power estimate over here is to get an idea of how much power, how much energy it's going to take to make the cut. Our look at power here is really to understand the forces so that we can limit the forces. So forces impact us, one, with the tool breaking, right? With the tool wearing out faster if the forces are higher. The part staying in the fixture if the forces are higher or lower. And the part deflecting and or the tool deflecting. And so one of those things that happens when the part and the tool deflect is they get pushed out of the way. As it gets pushed out of the way, the cutting's less efficient. The cutting force maybe goes down. And then if the force goes down, it bends back, right? And then it bends out because the force goes up, but it bends back. And it bends out, and it bends back, and it bends out, and then you set up a vibration. And so we'll very often have chatter in our machining operations, this vibration that's caused by that force buildup and then relaxation. All right, so we got, and all of it happens right here at the shear plane where it becomes, where workpiece becomes chip. So where do we see forces in this equation? Yeah. So we've got a force from the tool pushing on the chip or the workpiece, right? Oh, if it hadn't hit the ceiling, it would have been perfect. All right, so there's a force from the tool on the chip. And it's this resultant force. Some of it's component in this direction, some of it's a component in this direction. If we look at the chip interacting with the tool, what does the chip want to do with relation to the tool? So the chip has relative motion with the tool, right? So here's the edge of the tool, and the chip is moving that direction. So we've got friction right here, right? So there's friction on that surface. So one component of this resultant force has got to be able to line up with that friction force. And so there is a force here. And then what causes friction? Yeah. A normal force, right? So there is no friction if there is no normal force. Everybody else duck. There is no friction if there is no normal force, so there must be a normal force too then, right? So if the friction, let's see, the chip's going that way, so the tool's pushing on the chip back down this way, and there's got to be a normal force here perpendicular to the friction force, right? We got our normal force, so again, we're engineers. We don't have very inventive names for our forces and things. So what do you think we should call the friction force? Let's call it F. Sweet. What do you think we should call the normal force? Right? And F and N add together to make P. Not the way I drew it, but in reality, F and N add together to make the resultant force. Because there really is just this resultant force of the tool working on the chip working on the tool. And those are equal and opposite. Does that make sense? Okay, so, but we can divide it into this orthogonal force system of friction to normal. And, all right, so we did FC and FT earlier. We've got our friction to normal force. I didn't quite draw it at the same angle, but whatever. The angle I drew works better. See, these slides were a different shape. They were like not the wide format slides. And when I imported them into this presentation, all the pictures got stretched. So pay no attention to those angles. I want to get to the one with the equation. Come on. Here we go. Put the screen down. right. Room control down. All right, so let's talk about modeling of manufacturing processes again, just for a second. Why do we do it? Quickly, somebody, quickly, why do we model manufacturing processes?
So we can get an idea of how we can probably work.
So we can get an idea of how it'll work, but really we do it because we want to do it faster. Does that make sense? We model these processes because we want to figure out how to do it faster without having to try every idea that comes to our head. So if we get an idea and we can mathematically check if it's going to make it faster, we're going to do that. And so most of the advances, the significant fundamental advances in understanding how this chip formation works and understanding how this process works. And again, this is one of the most important manufacturing processes in the world today still. Most of the advances happened in the 1930s and 40s. Most of what we know happened and was discovered in the 1930s and 40s. Why? I heard World War II over here. Was that what you were going to say? That was what you were going to say too? Somebody over here? Okay. This is really hard for me. The mask makes it easier. I probably won't throw that one to anyone now. But I will run it through the washing machine later. I'm at the end. Today is the end of a 3-day fast. And so it's really hard not to eat this candy right now. All right, so this guy named Merchant, he came up with this relationship between the shear angle. And so the shear angle, again, is the angle at which we're going from workpiece to chip. And so that really has a significant the power of cutting is significantly impacted by the machinability of the material, which will help determine what the shear angle is going to be, and also by the uncut chip thickness, right? How big of a chip are we going to make? And so changing this shear angle can allow us to optimize the speed of the cutting operation. And so if we go back to look at the friction forces, if I go back a couple slides, you'll see that this tau is the friction angle. So it's the angle between the friction force and the resultant force. So that tau is that friction angle. And he figured out, and again, this is with degrees. So the shear angle is going to be 45 degrees minus tau over 2 plus alpha over 2. And so we can determine the friction angle, or rake angle we choose. That's a process variable. We choose what the angle of the tool is relative to the cut. So we choose rake angle, and we can determine the shear angle, or the friction angle. Go back up here. Maybe it's the other direction. So that friction angle, mu, so mu is the friction coefficient, right? So mu equals tangent of the friction angle, and it equals F over N. So we can figure out what that friction angle is if we know these things. Back to here. Merchant figured this out. We also know from the geometry, I got to stop making these fancy slides, that from our cut chip thickness, our uncut chip thickness, we can get that ratio. We can figure out what the shear angle is. So again, we can have two different ways to find out the same variable that can help us in problem solving. We're going through this shear angle, friction angle. There's a bunch of relationships that have been developed over the years. I could have you derive all of these, right? That could be your homework. It could be, though. But there's a very serious reason why it won't be. Because then I would have to check your work to give you the grade, and I don't want to have to do it either. So we're going to take this on faith from the engineering texts. We're going to take this on faith from the people who did the experiments already, and we're going to use the knowledge that other people created by doing their modeling. Does that sound fair? So engineers typically don't work in a vacuum. Does that sound fair? Has anybody ever applied for an engineering job? There's a career fair going on. Was that yesterday or today? Yesterday. Anybody apply for a job at the career fair? So at that career fair, they were very particularly looking for people in college, right? Because they came to a college to do it. But if you look at jobs for engineers, they often say 5 years experience required. You ever looked at a job and be like, I could do that job, but I can't show that I have the experience? It happened to me when I was coming out of college very often. There's a reason the companies want you to have 5 years experience. And it's because engineers don't need to know any, write this down. Engineers don't need to know anything. They need to know which book to look in. And so they wanted some other company to buy you all of the books. It's less important now that we have Google. I guarantee you that there are no quiz questions or exam questions that I will give you that you can't use Google to find the answer. You did know that all of our quizzes, exams, and stuff like that are open book, open notes. In fact, all of them except for the final exam, I encourage you to talk to each other to explore the answers. You should understand it because you're going to get tested on the final exam. But so we're going to use the information other people developed. A lot of what I'm talking about today is learning how to use that and how to find it. And so we got our machinery's handbook for things like modeling and understanding the power, estimating that. And that brings us to our closing topic today. What week is this? Week 3? Right, we're at the end of week 3. So then it's does that make this like, so Wednesday is hump day, so does that make this hump week for the term? Who's got midterms this week or next week? About half of you. Yeah. This ties back into engineering and to manufacturing, believe it or not. What is stress, though? And what is the stress that those midterms bring? What is the stress that having to wear a mask in class brings? Right? This has been a pretty stressful couple of years for everybody, for the world. What is stress? Yes. So pressure. So he says stress is pressure. What are the units for pressure? Newtons per meter, pounds per square meter, right? That's what he said. So newtons per meter, pounds per square inch. Let's do PSI, because I'm an imperialist. It's the imperial system, right? That makes, if I use those units, that makes me an imperialist. If we say PSI is pressure. Now, what's pressure mentally? What causes pressure mentally or mental stress? Yes. So work to do, things to do, is that like, did you also have an answer? Expectations. So people have expectations. You said lots of work to do, meaning more than you feel like you have the capacity for. So there's there's expectations, there's lots of things to do, maybe the feeling that you can't get them all done. So that's stress, right? Engineering stress, we like to give it units of, what is this? Force over area. So stress is really force over area. It's that pressure. It's the feeling, it's the feeling that the stuff takes, right? So I'm applying stress to the stool right now. I'm applying a force over an area. The area is roughly the area of my hand interacting with the stool, right? What happens when you apply stress to something? Yes? It strains. So what's strain? He's going to throw a piece of chalk at somebody instead of candy. So strain is deformation. So strain is deformation. So pressure or stress, this force over area, that acts on something. The strain is how much that thing that gets acted on changes. Does that make sense? And so if we look at it in engineering terms, so we got our force over area. And so here, if I got a round rod that I'm pushing on the ends of it, so my force is on the ends, the area is pi r squared, right? Cake r round, pi r squared. The chuckle was worth a piece of candy. What's that? Do you get it this time?
Yeah.
That's bravery right there. To announce to the world that you didn't understand something before and now you do. That's courage. It's overcoming strain, right? So strain is the result of stress. Yeah, cool slides. Yeah, okay, come on. All this fancy stuff. I hate that fancy stuff. I don't know what I was thinking the day I made those slides. I think I made those slides during the COVID shutdown. It was a dangerous time to be sitting in front of a computer. It was either make fancy slides or watch more Netflix, right? And there's a limit to how much Netflix you can watch all in a row. So we'll measure our stress, we'll measure our strain by comparing the length if we're pushing on something. How much does it change in length? And so there we go. We get cool equations. This is the fun part of the class because there's math. I have a theory about stress reduction. Because we'd all like to reduce stress, right? What's stress again? It's force over area, right? If you want the stress to go down, what can you do? I could reduce the force, right? Who said reduce the force? And you said reduce the area? Or increase the area, right? So I have this theory. See if my fancy slide works. So this happens, right? We get under high amounts of stress, we eat too much or drink too much. We do things that make us fat. So people, just like engineering subjects, can be impacted. All right. So it helps you remember. That's the theory. I read a book. I'm always trying to do a little bit better in my public speaking and in my lecturing, because I feel like if I go here and say, look at the slide and do this and follow the slide, you might as well just read the book. I'm not adding any value at that point, right? And it's no fun for me either. And so I read this book. It's written by the guy who at the time was the head of Sony Pictures. And so he's in the Hollywood, in this industry, and it's all about storytelling, right? And so he's talking about how to tell stories to influence people to believe the things you want them to believe. And so that book inspired me a lot, but he talks about a college lecture that he was in. And throughout the entire lecture, and so this was in cinematography or whatever, some filmy class, right? Some liberal arts thing that I guess pays well if you become the head of Columbia Pictures, but not otherwise. Or it was Columbia, Sony Pictures, whatever it was. Sony bought Columbia. That's how it got there. Anyways, he's talking about this lecture, and the professor's walking around the classroom up on the stage. It's a big like amphitheater full of students. And as he goes through the lecture, he's undoing his shirt, takes his shirt off, lays it on the chair. And then he takes his t-shirt off, lays it on the chair, kicks his shoes off. He's just teaching the lecture. By the end of the lecture, he's standing in front of the classroom in his boxer shorts. The point was, emotion will help you remember things. And so he said, nobody in this class will ever forget this lecture. And so I'm not going to quite go that far, but I may throw stuff at you. Also, throwing stuff at you keeps your reflexes alive, keeps you a little bit more alert, especially if you're near the person who spoke. So the requirement today to get a piece of candy was what? Answer a question. On Tuesday, there'll be candy left over. It's a big bag. On Tuesday, what's the requirement going to be, do you think? I'm going to want you to answer correctly, at least in my opinion. So today I didn't care what the answer was. Tuesday, I'm going to care if it's correct. If there's still candy left after that and I still remember to bring it, it'll have to be a correct answer and I'll have to think the question was important. So we've got just a couple minutes left in the class today. Groups, because it's going to be a group project. I'm going to give you the assignment for the group project. Before I do that, though, I got to show you how to get in a group. So I am sending this out online. Okay, good. So groups. So we'll go to Canvas. People. Groups. I'm creating a group set. There's what, 72 people in the class? There's supposed to be 72 people in the class. A group set name. What's a good name for a group set? Group. Okay, good name for the group set is group. I am going to allow self-sign up. I'm not going to require group members to be in the same section. Limit groups to 3. I could be lobbied right now to go to 4, but I really hate groups of 4. So if there's 72 people, is 72 divisible by 3? Yes. There's totally not 72 people. Somebody must have dropped. Somebody's not coming anymore. Only 69 people have submitted the last assignment. So is that still divisible? It is. Hey, so it should work out. Okay. If for some reason you can't create a group of 3, at most there should be one instance, well, maybe 2 instances of this, that you can't create a group of 3. I will allow up to 2 groups of 4, but don't ask me to be a group of 4 unless you can prove that it's impossible to create another group of 3. Because I have to manually go in and edit the group to add a 4th person to it. Let's see. So limit groups of 3. How many times does 3 go into 72? 75. How many times does 3 go into 75? What's that? 25? Yeah. I'm going to create 25 groups. That way there's more groups. There's definitely more groups than there is possibility of students in the class in groups of 3. Be together with your group of 3. Log into Canvas, add yourself to the group. And then log into Canvas, add yourself to the group. This is a process. You can do that. Save. Okay. Group set is created. Do not create your own group that's outside of this group set. Join one of the groups I just created. Otherwise, when I do the group assignment, it will not be assigned to you and you won't get credit for it if you hand it in, even if I grade it. So join one of these groups. If you're having trouble finding people to be in a group with you, discussion. This 71? Yeah, but only 69 people submitted the last assignment. So Discussion. Finding. Reply to this. You need help finding a group. Okay, so go to the discussion forum, reply to the finding a group thread if you're having trouble finding a group. Before you reply to the thread, though, look at the other replies and see if you can just form a group there. Make sense? Okay, and I still owe you the quiz. I promise it'll be posted today, and it won't be due. I'll figure out a due date that's reasonable.